Okay, welcome. This is the second part of the lesson over section 3.2 in the textbook. I know it says lesson 3.3, but it is over section 3.2 in the textbook. And we're going to continue talking about our least squares regression line, some things that go with it. Okay, so a new vocabulary word is residuals. Residuals are basically the error, the distance, the vertical distance between a point and the predicted value, the least squares regression line. So it's the distance between the linear model's prediction and the observed value or the actual value. I like to use the word actual, but observed is accurate also. So it's the observed value, which we use just the letter y, minus the predicted value. And remember, predicted value is the y with the hat on it. And to keep the order correct, I always think of actual minus predicted, it's AP. So you're in an AP class, so it's actual minus predicted. So let's take a look at what we were exploring last time, and that was how attendance affected the math star scores. And I'm just going to take you down through here. So we had this least squares regression line of the predicted star test score is equal to negative 7.69 plus 0.57 times the attendance percentage. So if I have someone and I know what their attendance rate is, I can predict what their test score would be. And so I'm simply taking that attendance rate and plugging it in for the x. And we get a predicted value of 37.91. Now that's the prediction, but let's say the student takes the test and gets 44 correct. Awesome. Must have a great math teacher. But we want to look at the error now. So the error is called the residual, and we get that by looking at the actual minus the predicted. So the actual amount minus the predicted score. And so we get a residual of 0.609. And we would write that as the actual test score is greater than the predicted by 6.09 points. And notice we have this thing here, the STEM for interpreting residual. Anytime you see this in the notes where it says STEM, this is going to be the format of how we answer questions about interpreting residuals. So if our residual is positive, that means that the actual response variable is greater than the predicted by the residual amount. If the residual is negative, it meant that the actual response variable is less than predicted by whatever the residual amount is. Okay, so that's just an example there. And let's talk about what residual plots look like, because these are going to be very important. So here I've got speed and stopping distance. So depending on what speed I'm going, how long does it take to stop? And here's the least squares regression line. And just like we saw last time, this distance from the point perpendicular, or not perpendicular, but straight down to the least squares regression line, that is what we call our residual. That distance we can now graph. So my residual plot, along the x-axis, I have my speed. Along the y-axis, I don't have my stopping distance. I have the residual, which is the actual value minus the predicted. And if you take a look here, these first two data points are both above it, so they both show up here as above the zero. This third point here was below, so it's going to show below my line of zero. And the last point over here is above, so it shows above zero. And this is my residual plot. Residuals should be randomly, that should be randomly, not random, so randomly scattered around zero without a pattern. And if they are randomly scattered around the line y equals zero, that tells you your linear model was a good fit. So you want to see random data in your residual plot. Here's what happens if it's not linear data. So here's my data, my explanatory and my response, and that looks like a pretty good fit. But when I plot my residuals, notice that they form a curved shape. Not perfect curve, but a curved shape. That tells us, so when we see this curved shape, it tells you the linear model is not a good fit for this data. We don't have to say what would be a good fit, just that the linear model is not a good fit. Another thing that would tell you that a linear model is not a good fit is if you have what's called heteroscedastic data. So again, here's my explanatory and the response. The line goes right through here, the least squares regression, and here's my residual plot. So notice the points are closely clustered around 0, but as x gets bigger, they get further and further away from 0. So they're growing. That also tells me that the linear model was not a good fit. So again, residual model, we want to see random looking data. Or residual plot, not data. Okay, as we continue talking about this, there's a few other things. Oops, let me get to the right page, the next page. We want to talk about the standard deviation of residuals. We use the letter S here. So we know we've talked about standard deviation with our normal data, and that's the typical distance between your data point and the mean of the data. So standard deviation of the residuals is the typical error between the data point and the least squares regression, or the typical residual. That word typical we want to be using. So let's look at this chart A. Notice the line, least squares regression line, all the points are very, very close to it. S represents the typical residual length. So these are pretty tiny lengths, right? So there's the typical length. That tells us we have a stronger correlation because it's a very small standard or typical residual length. Chart B, the residual length, they're all bigger. So the typical residual length, S, is bigger. That tells me I have a weaker correlation. So a weaker correlation has a larger S value. A stronger correlation has a smaller S value. So it's clustered close together. That's similar to what we saw with normal data too. Okay, here I've got my same data looking at the percentage of school days attended versus your STAR Algebra 1 score. And I'm telling you that the S value is 1.99, and we want to interpret it. Again, we have a stem, our sentence that we want to use for interpretation. And the stem would say, when using the least squares regression line with whatever your explanatory variable is to predict the response variable, we will typically be off by about whatever your S value is. So in this case, we just plug this in so I don't waste time. When using the least squares regression line with attendance to predict the Algebra 1 STAR test scores, we will typically be off by about 1.99 points. So again, you're just plugging things in for everything that's underlined on here. Okay, before I go to the next part, this next part we're going to be talking about something that may be a little bit disturbing. And if so, you don't have to listen to this. Just copy down the notes or read through in the textbook, section 3.2. But what we're going to be talking about is mass shootings in the United States versus 3 things that are often associated with mass shootings and predicting them. And those 3 things are video games, amount of guns in the United States, and mental health. So we're going to take a look at all 3 of those things and see what we can find out in our data. So now taking a look here, I've got the number of shootings by the year, the number of rifles that were manufactured in the U.S., the number of U.S. residents with mental health disorders, and then the revenue from the U.S. Video game sales. One thing about the mass shootings, we're defining that as having 4 or more victims, and that there was indiscriminate targeting, meaning that this was not something that happened in a private residence where someone was specifically targeting a spouse or whatever the case may be. Also, it excludes ones that the violence comes from another crime, such as robbing a house or something. We also list where all the data comes from. A good statistician always tells the reader where the data comes from. And what we are doing here is along the x-axis, we're putting in the different explanatory variables. So rifle production, mental health disorders, and video game sales. The response variable is the mass shootings, the number of mass shootings. So same time periods, and you can see we've got 3 different charts. They all are linear, they all are positive, and the strength is different here. One way, again, we can look at this in terms of measuring the correlation is what is our residual, the typical residual error. And I'm telling you that the typical residual error for rifle production as the explanatory variable is 1.31. The typical residual error for mental health is 1.69. And when we're talking about the typical error, the S value, we want a smaller value. So compared to mental health, rifle production is a stronger predictor of mass shooting frequency. And again, that's because it has the smaller S value there. Okay, and let's move on to just more generic ones now. Let's take a look at some different correlation graphs which we've seen before. And we had our R values. Remember, R can go from +1 down to -1. But now what we're going to look at is taking that R value and squaring it. So 1 squared is 1. 0.91 squared gives us 0.83. And on through here. The one thing that does happen is that all these negative values now become positive. Because remember back, whenever you square a negative number, you get a positive. So this R squared value is called the coefficient of determination. And we can get that off the calculator. Typically, in an AP test or exam, you will be given these R values or R squared values. If I gave you the R value, you could find the R squared by just squaring it. If I gave you the R squared value, you take the square root. However, you'd have to be careful to make sure whether you're taking a negative square root or a positive square root. And that would be based on what direction your data is, what direction the correlation is, if it's a positive correlation or a negative correlation. And when we square these R values, it gets rid of all our negatives, but it also emphasizes the difference in strength. Because we're doing values that are between 1 and -1, that the numbers get smaller as we square them. So going from 0.48 to 0.23. So it's exaggerating that difference in the strengths. My R squared value can only be between 0 and +1. So if we have an R squared value close to 0, it's a very weak correlation. If it's close to 1, it's a strong correlation. Notice it doesn't tell us if it's a positive or negative correlation, just that it is strong. One of the key things here is how to interpret the R squared value. And again, we have a sentence stem here. So when we put these in, we're going to say the R squared, the percentage, so like 23% of the variation in your response variable can be explained by the linear relationship with your explanatory variable. So if my R squared value is 100 or 1.0, that means 100% of the variation is explained by the model. If we have an R squared value of 0.72, it means that some of the variation in what we get for Y based on your X can be explained by the linear model, but not all of it. 72% can be explained by the model, which means that 28% of the variation cannot be explained by the model. There's something else causing it. If we look back at our number of rifles manufactured versus our mass shootings, the R value here, the R squared value is 0.62. So with an R squared value of 0.62, again, I'm going to plug it into here. So 62% of the variation in the frequency of mass shootings in the United States can be explained by the linear relationship with the number of rifles manufactured in the United States. So again, the variation in the Y value can be explained, 62% of that variation is explained by the linear model here. Okay, so here's the one we were just looking at. If we were looking at versus mental health, 36% of the variation can be attributed to this linear model. So that's much weaker correlation. Video game sales, 69% of the variation can be accounted for or attributed to the video game sales. So video game sales were the strongest predictor of the annual frequency of public mass shootings in the US because it has the highest coefficient of determination. Remember, S is the typical error in the residuals. R squared is related to our correlation. So if I look at this chart A, it's a fairly strong correlation. So that means I have a low S value, but a high R squared value. On this one, we have a larger typical residual value. So that means we have a higher S value, the typical error in the residuals, and a lower R squared value. And if you remember, when we talk about describing the relationship between the explanatory variable and the response variable, there were 4 things that we hit. And those were the form, the direction, the strength, and then any unusual things, namely outliers. So let's take a look at some outliers here and see what happens. So if I am looking, let's say on chart A, so this point is part of chart A. It looks like that's an outlier, but if I were to extend that least squares regression line, that point is right on that line or really close to it. So that's not an outlier. It lines up with the other points relative to the least squares regression line. Okay, chart B. Looking at this, these 3 points are all extremely close to my least squares regression line. This point is quite a distance from the least squares regression line. So I would call that an outlier. Chart C, this point is the one they want us to look at. If we look at the distance, again, the vertical distance to the least squares regression line, that looks like about the same distance some of these other points are. So I would not call that an outlier. Okay? So that's how an outlier works. It's one that doesn't follow the same pattern. Here we're looking at the rifle production as the explanatory and public mass shootings as my response variable. I have taken off this point from the year 2017 because it was an outlier. It's unusually far away from that least squares regression line. So if I take out the outlier, here's my correlation coefficient, the coefficient of determination, and my residual error. With the outlier, notice my correlation goes down, my coefficient of determination goes down, and my typical error goes up. So all 3 of those values are not resistant to outliers, meaning that outliers have a great effect on them. Outliers lower the strength of a relationship, making R smaller, R squared smaller, and S, the typical error, larger. Okay, so a couple things to think about. For our video game sales versus US public mass shootings, would it be fair to say that banning violent video games would prevent more mass shootings and banning assault weapons are improving mental health services? Why or why not? Just give that some thoughts. And one thing to keep in mind, these are showing correlations, not causations, right? So far in this course, we have not discussed how we show causation. So again, here I've got my years and the number of shootings, the years and the video game revenue. If I were to overlay these on the same chart, you can see that they sort of coincide. They go in the same direction, the trends, which should remind you of this chart we had where we talked about the number of films that Nicolas Cage appeared in versus the number of people who drowned by falling in a swimming pool. It was very tightly correlated. I believe, if I remember correctly, it was like 0.95 was the R value. But obviously, Nicolas Cage appearing in movies does not cause people to drown by falling in their pool. So correlation is not the same as causation. So we have to be very careful, coming back to this question, about assuming by just banning that we would lower the mass shootings. We haven't shown any causation yet. Okay, and that is it. Go ahead and you're going to take a look at the homework and feel free to ask me if you have any questions. Thank you.